India will be presenting my paper titled Remedial Action Scheme for Wind Power Injection Considering Power System Inertia. The share of renewable energy sources, especially wind energy, is increasing rapidly in the modern power grid to cope up with the devastating impact of climate change and global warming. The increment results in reduction in the network inertia. Inertia plays a vital role in determining the immediate frequency response after a disturbance. It provides the necessary energy buffer to the grid operator for smoothing out sudden power imbalances. The inertia for the power network is estimated using swing equation given by equation 1, where F0 is the nominal system frequency, Pm is the total mechanical power of the synchronous generators, Pe is the total electrical power of the synchronous generators, S is the nominal apparent power of the system, dF by dt is the rate of change of frequency. For a network with G synchronous generators, the network inertia H is defined as summation over HI by SI, where HI and SI are the inertia constant and the rated apparent power of the IL generator respectively. Now moving forward to the problem formulation. The objective function defined in 3 aims to maximize the wind power generation from wind generator subject to 5 constraints. The 5 constraints are listed from equation 4 to 8, where equation 4 maintains the active power balance in the network. Equation 5 and 6 keeps the active power generation and bus voltage angle between its limits. Equation 7 and 8 maintains the frequency and network inertia between the operating limits. Here, Pij is the active power flow through line connecting buses I and J. Pig is the bus I active power generation. Similarly, PID is the bus I active power demand. H is the network inertia, N is the number of buses. So the methodology says that initially the maximum and minimum inertia is calculated using offline network data such as load data, generator data, and the line impedance. Following this, the rate of change of frequency using the historical data of disturbances on the network, a polynomial fit curve is obtained, which is used to extrapolate the rate of change of frequency for similar disturbances. The initial conditions are evaluated using the online PMU data. If any of the constraints listed from 4 to 8 are violated, then the remedial action scheme will not trigger because the basic constraints for the power system is being violated. If and only if the constraints from 4 to 8 are not violated, the remedial action scheme will be initiated and the optimum generation value from the wind power generator will be calculated, and for that specific network inertia, the maximum wind power generation will be obtained. The scheme is tested on the WSCC 9-bus network, which consists of 3 generators, 3 transformers, and 3 loads. The total network inertia is 3.3717 seconds, and the total load is 315 megawatt and 115 MVAR. Here, as shown by the graph, you can see that as the wind power generator output is increasing, the network inertia reduces. The network inertia, for a network inertia of 2 seconds, the optimum wind generator output is 179.8 megawatts. Similarly, as the network inertia increases, or we can say that as the wind power generation decreases, the network inertia increases, and vice versa. The results are validated on PSCAT EMDDC, where a 3-phase fault at 2 seconds for 0.2 seconds is simulated on the network with 3 different amount of wind power injections. The network is similar to the previous network, which is the WSCC 9-bus network. The fault occurs on the line connecting buses 7 and 8 at a distance of 50 km from bus 7. To check the stability of the network, a fault current through the transmission line and the angular difference between the bus voltage at bus 7 and the slack bus is used. Here you can see that as the wind power injection is 50 megawatt, from 2 to 2.2 seconds, the fault is occurring on the system, and after the fault is being cleared, the system is stable. Here 50 megawatt of wind power is injected into the system, which shares 15.873% of the load, and the network inertia reduces to 3.189 seconds from 3.3717 seconds. Similarly, as we inject 100 megawatt of wind power injection, which accounts for 31.746% of the load, the network inertia reduces to 2.937 seconds, and the fault current and angular difference graph can be seen, which is not quite stable as for 50 megawatts. Further increasing the wind power injection to 200 megawatt, which accounts for 63.492% of the load, the network inertia reduces drastically to 1.873 seconds, and as shown from the graphs, it is quite logical that the system is reaching at the verge of instability. For concluding my presentation, I would say that this method is used to increment the amount of wind power injection in the network. It reduces wind curtailment to a considerable amount. The proposed algorithm are adapted with the existing network and offers viable and economical solution. It reduces carbon emission. The future scope of our work is to optimal placement of battery energy storage system for increasing network inertia and sizing the BESS to maintain required inertia in the network. If the network operator wants a network inertia of 2.0 seconds in the system, and due to the wind power injection it reduces from 2 seconds, then the BESS can maintain it back to 2 seconds. That is what our aim is to do in the future. Thank you.
Okay, well, thank you everybody for